Hello friends, I am Dr. Prabjit Singh. From this week onwards, we will be mostly working in MATLAB and Simulink environment. I hope you must have tried or simulated examples in MATLAB taught by Professor Deepak Giri. Now we will be focusing on simulation of mass spring damper system. But before that, we need to quickly revise some concepts of first and second order systems. And why do we need to do that? Because mostly practical systems can be represented in first and second order systems. Consider the example of an aircraft. The 6 degree of freedom aircraft equations of motions are represented in first and second order form. Although this form has been transformed from second order Newtonian dynamics by introducing additional state variables for velocity and orientation rates. Let us begin with the first order system. The representation of the scalar first order differential equation can be represented as dy by dt equals to function of t comma y comma u, where t is continuous time variable u equals to u of t represents system input, f represents the derivative function, y equals to y of t represents the system output. Now consider a case where f is a function of input and output by f of t comma y comma u equals to b naught into u of t minus a naught into y of t. We will consider this as an equation 1, this as equation number 2. So here a naught and b naught are considered as constants. We can write dy by dt equals to b naught u of t minus a naught y of t. Now since a naught b naught are constants, and the behavior is linear, the equation is said to be LTI, which is nothing but linear time invariant ordinary differential equation, ODE, that is ordinary differential equation. Now we can write the above equation as y dot plus a naught into y equals to b naught into u. I am dropping the t terms for convenience. Taking a naught common, 1 upon a naught into y dot plus y equals to b naught into u. I can represent this as some variable tau into y dot plus y equals to some k into u. We'll understand the significance of tau and q in a minute. Here tau is 1 upon a naught and k equals to b naught upon a naught. Now consider an input to be a constant, that is u of t equals to some constant a. In terms of aircraft, you can assume the elevator is, for example, elevator is around 2 degrees for all time greater than 0. Then the solution is obtained by either using classical time domain methods or by Laplace transform. Now let us learn how to the differentiation in this equation in MATLAB. Now let us switch to MATLAB. Now this is how the MATLAB environment looks like. I have already written the equations. I will not rewrite it again to save time. Now this is CLC, clear screen, close all. It clears all the variables and closes any figures if there is any open figure. And I am defining the symbolic variables SYMS. The variables are y of t, a, k, tau and y naught. Then I am defining the differential equation y dot equals to diff y comma t. The syntax for defining any differential equation is diff. If you want to know more information about diff, we can simply write in a command window help diff. We can also open the documentation if you like. So this MATLAB function calculates the differences between adjacent elements of x. The syntax is diff of x. I have used here diff x comma n. Here x is the input array, n is the difference order, positive integer scalar. Next, I am defining the step input u equals to a, and finally the differential equation with initial condition y of 0 equals to y naught. The equation is represented as tau into y dot plus y equals to k into u. This is the way of defining any equation in MATLAB environment. Now we will find the solution of this differential equation directly in MATLAB. Solve the differential equation with the given initial condition. I have written y solution equals to d solve. Again, if you want to know information about d solve, you can look it here. Solves the system of differential equation. This function solves the differential equation where equation is a symbolic equation. So I have removed semicolon here. I just want to show here what is the solution of this differential equation. If I run this program, then the solution comes out to be e power minus t by tau into y naught minus a into k plus a into k. Let me write the solution here. Y of t equals to e power minus t by tau y naught minus a into k plus a into k. This can be further written as e power minus t by tau into y naught minus e power minus t by tau a into k plus a into k. Y of t equals to y naught e power minus t by tau plus a k. I am taking this as common, can be represented as 1 minus e power minus t upon tau. Now what we'll do is we'll plot this solution in MATLAB for different values of tau. Now let us switch back to MATLAB again. Now I've considered few variables here. Here gain k is given as 5, a is given as 2, y naught initial condition is 0, and the time range is from 0 to 50 seconds with the frequency of 500, and different values of tau I have taken as 0.5, 2, 5 and 10. Now I am trying to plot this response. I have named it as figure 1, hold on. Then I have written a for loop for tau value equals to taus, which is 0.5, 2, 5 and 10. And then I am substituting these values into symbolic solution. I have named the variable as y numeric equals to subs. It will substitute in this equation y solution. This is the old variable and this is the new variable. Again, to get more information about these subs, you can simply write it here, help subs. So this is the syntax subs s, that is the equation, then is old and new. Then after this we need to convert this symbolic expression to a function handle for evaluation. That can be done by simply writing MATLAB function and of bracket y numeric. Then finally we evaluate y of t over time, y vals equals to y function of t, and then we plot t comma y variable. We have here display name tau equals to, I am converting this numbers to string, tau value represented in seconds. Then finally I am plotting it with x label as time second, y label is in y of t, title is response of first order system with different time constants. I'm showing the legend as show, grid is on. I'm running this code. So this is what we get after running the code. So we observe here we get different responses for different values of tau. Now let me just explain the figure here. So this graph of y of t is called step response. Because the input resembles a step. And also we can note here that y naught is 0 for all cases. Here A represents amplitude of the input, which is not a system parameter. K and tau are actually system parameters. That is, they are a function of A naught and B naught. Here K is called as steady state gain. If we see y of infinity, if we substitute infinity in this solution of this equation, we get y naught into e to the power of minus infinity, and we know to the power of minus infinity is 0. So y of t equals to 0 plus a into k into 1 minus 0. So finally, what we get, k into a, and I have considered the values of k and a as 2 and 5. So we get y infinity equals to 10. So we observe that final value, if we see the plot here, we observe that the final value y infinity is unaffected by y naught. However, the graph starts from y naught. Another parameter is tau, where the graph is different for all the four values. So there is a noticeable, if you see the figure here, so there is a noticeable difference in the amount of time required for the response to reach y infinity equals to 10. So we can call this tau parameter as time constant of first order system. It is a measure of speed of step response or overall speed of first order dynamics. Now, when in terms of aircraft, higher gain k means larger steady state output. Here output can be, for example, pitch angle or altitude change. So higher gain k means larger steady state output for same input that is high gain k for pitch response could result in larger change in pitch angle. Per unit elevator input. Similarly, the time constant tau indicates how quickly aircraft, I am representing aircraft as A by C, aircraft can reach that steady state pitch angle after the control input. Hence, we can infer that both k and tau are important parameters for defining the aircraft control systems. Now, we will move on to the second order systems. So, linear second order systems can be represented as d square by dt square y of t plus 2 zeta omega n d by dt of y of t plus omega square n y of t equals to k into omega square n of u of t. Now consider this as an equation number 4. Now, the second order systems were talked at length by Professor Deepak Giri in the first course. I will only touch upon the basics so that we can easily apply those equations in the MATLAB Simulink environment. So, we will continue from here. We will stop it right now. We will continue from here from the next lecture. In the next lecture, we will be talking about more about the second order systems. Thank you.